We'll come back to Gibbs sampler later on when we see a Bayesian example. For now, let's talk about some methods for monitoring chain convergence in MCMC. One challenge of MCMC is knowing when the chain has converged to its stationary or target distribution. This will determine how long should we set the burn-in cycle to be. Intuitively, if you set the burn-in to be too long, it means that you need to run your chain for a really long time. In practice, MCMC is usually computationally intensive, and running it for a long time can take a lot of time. On the other hand, if you set the burn-in cycle to be too short, then your post-burn-in cycles might not have converged to the stationary distribution yet. Doing posterior inference before convergence can lead to biased parameter estimates and incorrect inference. There's a lot of ongoing research on methods for determining and monitoring chain convergence. However, we will just discuss one popular and classic method here developed by Gelman and Rubin in 1992. The idea of the Gelman-Rubin method is as follows. Suppose that you recall that when you do Metropolis Hastings or Gibbs, you need to simulate a chain with a particular starting value. The starting value is quite arbitrary, and ideally, when your chain has converged, then even if your starting value is quite far from the stationary distribution, then after a long run, your samples should be approximating and getting closer and closer to the target distribution. So the idea is as follows. You are going to generate multiple chains, multiple MH or multiple Gibbs chains, each with different starting values. Ideally, the starting values should be far away enough so that each of them starts at a really different place. If after n cycles, a chain has converged, it means that no matter how far the different chains have started as, in the end, they should all get into a similar place, which is the stationary or the target distribution. So calculation of the Gelman-Rubin estimated potential scale reduction, denoted rhat, which is a lot shorter than EPSR, proceeds by generating multiple chains with different initial or different starting values. Suppose we generate k separate chains. Each of them has a total of n iterations. Let us denote all of the draws across the k chains by the set xij, where I ranges from 1 to k, indicating the chain index, and j ranges from 1 to n, indicating the iteration index. The different chains ideally have different starting values that are far away. Let psi denote a summary statistic that estimates some parameter of the target distribution. An example is psi is an average, in other words, the posterior mean. If we compute psi in, which is the psi statistic calculated for the MCMC draws from the first iteration all the way up to the nth iteration. For example, if psi is the mean, you take the average of the x's across the first to the nth iteration. Then intuitively, if n is large enough to reach convergence, we would expect psi 1n, psi 2n, and psi kn to be about the same, meaning that for different chains with different starting values, if your n is large enough, then the summary statistic you get using the draws from each chain should be similar. The Gelman-Rubin method compares the between-sequence variance of the psis to the within-sequence variance of psi. The between-sequence variance is defined as follows. It's given by n divided by k minus 1 of sum from 1 to k of psi I dot bar minus psi dot dot bar squared. Here, psi I dot bar is the average of the psi ij's within the ith chain, where psi ij is the summary statistic computed using samples from the first iteration to the jth iteration in the ith chain. For example, if psi is the mean, then psi ij will indicate the mean of xi1 all the way up to xij in the ith chain. And psi dot dot bar is the overall average. This is the average of the psi ij's across all iterations as well as all chains. So that's a pooled average. You can see the B, the between sequence variance, thus captures the square deviation between the mean of each of the separate chains with the overall mean across different chains. If B is large, it means that there is a lot of variation in the means across different chains. And here's the within sequence variance. Within the ith chain, the sample variance Si squared is given by this familiar formula over here. It is essentially the mean of the square deviation between each of the single psi ij's, j from 1 to n, and the average across all of these guys. We can get one of the Si squares for each of the chains. And then the pooled estimate of within sample variance is the average of Si squares across the k chains, and we denote it by W. As you can see, the within sequence variance captures the expected amount of deviation of one single iteration psi ij with the average of the entire chain. The B and the W are combined to obtain an estimate for the upper bound of the variance of psi. Let's denote this variance estimate by var hat. Var hat of psi is given by n-1 divided by n times W, the within sequence variation, plus 1 divided by n times B, the between sequence variation. If the chains were random samples from the target or the stationary distribution, then this var hat is an unbiased estimator for the true variance of psi. If the chains have not yet mixed well by time n, we would expect that within each of the chains with their particular starting values, W will tend to underestimate the variance of psi. And var hat, which is a linear combination of the within and the between sequence variations, will tend to overestimate the true variance of psi's. The Gell-Mann-Rubin statistic R hat is defined as var hat of psi divided by W. And this is called the estimated potential scale reduction factor. The R hat can be interpreted as follows. Square root of R hat has a name, so it is an estimator of the scale reduction factor, square root of R hat divided by var. So square root of the true variance divided by the square root of the estimated variance divided by the true variance. This thing is called the scale reduction factor, and it is the factor by which the standard error estimate of psi could be further reduced by extending the chain length. And R hat can be interpreted as a convergence diagnostic statistic as follows. If R hat is way larger than 1, so say it's 1.5 or 2, then it means that the ratio between var hat and W is large. Then further extending the chain would either reduce the variance estimate of psi, in other words, reduce the numerator, or increase the denominator W, in other words, increase the within chain variation. If the within-chain variability can be increased by making more MCMC draws, then it indicates that the current simulated sequences have not yet made a full tour of the target distribution. In other words, we haven't yet mixed well. On the other hand, if r hat is close to 1, we can conclude that each of the case sets of n simulated observations is close to the target distribution. So, what is a sufficient r hat for us to conclude that it appears the chains have converged? Gell-Mann suggests that r hat should be no larger than 1.1 or 1.2. Well, although he included the 1.2 option here, and although the textbook talks about the use of 1.2 as a threshold, in practice, I think right now people increasingly use 1.1 as a threshold. So if your r hat is below 1.1, then it indicates that it is possible the chains have converged. If your r hat is greater than this threshold, it indicates that you should run it for longer to reach convergence.